Right, so the topic is hypothesis testing. So we'll take a look at the syllabus first. So I've highlighted some parts of the syllabus yellow and some red. So first we'll be covering the yellow highlighted part. So I'll be reading that for now. Understand the nature of a hypothesis test, the difference between one-tailed test and two-tailed test, the terms null hypothesis, alternate hypothesis, significance level, rejection region, acceptance region, and test statistic. Then there is formulate hypothesis and carry out a hypothesis test concerning the population mean in cases where the population is normally distributed. Normally distributed is the keyword, with known variance or very large sample is used. Right. Understand the terms type 1 error and type 2 error in relation to hypothesis tests. Calculate the probabilities of making type 1 and type 2 errors in specific situations involving tests based on a normal distribution. So, if you have not noticed, we're right now and first we're focusing on the normal distribution. Then we'll go on to the Poisson or different distributions. So yeah. So what basically is hypothesis testing? So on the basis of, again, this is linked to the previous chapter, that is sampling and estimation, and you need to have a good understanding of that to understand this. So again, over here we have taken a sample from a population. The using this sample, we're proving and we have a certain value for the mean of the population, and there's a hypothesis that the mean is either greater than that, lesser than that, or not equal to that. Now we have to prove if it is true or not based on the sample data, right? So again, as in sampling and estimation, the distribution of sample means will always be normal in our syllabus. Either the underlying distribution will be normal, that was the first case in estimation that we did, in which we can directly say that this distribution of sample means is normal, or the sample will be large, in which case we'll be able to apply the central limit theorem and approximate it to a normal distribution. The other thing is that in some cases population variance won't be given, in which case we'll be using the unbiased estimate, which is again from the previous chapter, that is using n upon n minus 1 times the population times the sample variance. Right, so over here what will happen is that we'll be given a certain value for the mean. So our null hypothesis will be that the mean is equal to that certain value given, that is taken as mu naught over here. Right, now we'll assume that this is true. The null hypothesis will always be equals to, and it will be assumed as true. The alternative hypothesis will be, again, it will be hinted towards in the question. It might be that mu is greater than the given mean, mu is less than the given mean, or mu is not equal to. If it is greater than or less than, then that is a one-tail test, because it's either greater than or it's less, or it's either greater than, that could be one case, or it's just less than, that could be second case. If it's greater than, then that is an upper tail test. I'll be explaining what that means. If it's lesser than, that's a lower tail test. If its mu is not equals to the certain value, then that means that mu could be either greater than or lesser than. This is the two-tailed test. Again, I'll be explaining this more and it will get clearer with the questions when we try them. Next is the significance level. So significance level, again, this is given in the question. It gives the probability of rejection of null hypothesis. I should mention that, of H naught. This is used to find the critical value of Z from the table, from the normal distribution table, that is this table. Now we need to find a test statistic. This value is based on the sample that we've taken. This is the formula. This is the simple formula that we used to use in AS for a sample for approximating a distribution to a standard normal distribution. Over here the distribution is x bar follows normal mu comma sigma square upon n. So then to find z we use this formula. Okay, so now to understand this better, so what happens is, let's say there is a upper tail test in which we're given, for example, h naught is mu equals a, h1 is mu is greater than a, and it's given that test this at a 5% significance level. So because it's greater than, so that's why it's an upper tail test. We'll be testing on the right hand side, like over here. Now using the sample data, we find a certain value for z, that is the z statistic or z test value. And because it's an upper tail test, so, and the significance level shows the area of rejection, the probability of rejection. So what we do is that it's 5%, right? So the extreme right hand corner having a probability of 0.05, that is equal to 5%, will be the rejection region. So basically this whole region has a probability of 1. Now from this, the extreme right region containing a probability of 0.05 will be the rejection region. So this region, let's say, has a probability of 0.05. So using that, that means if it's 0.05 to the right of z critical value, then towards the left that will be 0.95. So if it's 0.95, so we can go to the table, get the value of z for 0.95. So 0.95, z is 1.645. So that means that this critical value, z test value we found from the data, z critical value we got as 1.645. Let's say that the z test value was 1.5. So the z test lies towards the left in the acceptance region. This is the acceptance region. This is the rejection region. So since z test lies in the acceptance region, so we will be accepting h naught and rejecting h1. If z test was, let's say, 1.7, so z test would lie towards the right of z critical value in the rejection region. So in that case, we would be rejecting h naught, accepting h1. I hope that's clear. So it's pretty similar in the lower tail test. The only thing is that because it's less than a certain, mu will be less than something in the alternate hypothesis, so we'll be going towards the lower tail, and the critical value will be taken negative. You'll get a negative test value, and then comparing that, we'll see again over here, this will be the rejection region. So if the test value lies over here, then the null hypothesis is rejected. If it does not, if it lies towards the right, then it will be accepted. The last is the two-tailed test. Now over here, it was a case where, let's say that the null hypothesis is again mu equals a. Alternate hypothesis is mu not equal to a, right? So it can be greater than or less than. Now if we given 10% significance level, then that means that we'll be dividing this by 2. 5% will be towards the right, 5% will be towards the left. Then we'll find the z critical value. These, because it's symmetrical, the normal distribution graph has 0 over here. So both values will have the same magnitude, only the left one will be negative, the right one will be positive. And then we'll find the test value. If the test value lies over here, the rejection region will be this part and this part. If the test value lies in the rejection region, then we reject h naught. If it lies in the acceptance region, we accept h naught. So questions will make this more clear. Okay, so the first question. The time taken for Samuel to drive from work is distributed with mean 46 minutes. Samuel discovers a different route and decides to test at the 5% level whether the mean time has changed. Whether the mean time has changed. Okay. He tries this route on a large number of different days chosen randomly and calculates the mean time. State the null and alternative hypothesis for this test. So H0 is the null hypothesis, H1 is the alternative hypothesis. So the null hypothesis is always about equality. So the mean time was 46 minutes, so null hypothesis will be mu equals to 46. And then it's given that he has to test whether the mean time has changed. So there's no mention of greater than or less than. That means that mu is not equal to 46. It's changed. It's either greater than that or it's less than that. We don't know for sure, but it's testing for both of them, right? So this will be a two-rail test. So first part done. Then Samuel calculates the value of his test statistic z to be minus 1.729. What conclusion can he draw? Okay, so this is a two-tailed test. So we can say that, and it's 5% level, so that means that each region should be 2.5%. This should be 2.5 and this should be 2.5%. Right. So now we need to find the critical value of z, basically this value. So for this value, we know that the area from here till here will be 0.025 plus 0.95. That is because this area is 0.95, 95%. Then converted to probability, that is 0.95, and 2.5% converted to probability is 0.025. So this is equal to 0.975. So this is the probability. We need to find the value of z at this probability. So 0.975 gives 1.960. So critical value of z is 1.960. So now what I can do is if I remove this, I can write over here that this value is 1.960 and this will be negative 1.960 because of the symmetry of the graph. The test value that was found, it's given directly, we don't have to calculate it, is negative 1.729. So negative 1.729 might lie somewhere over here. So it's in the acceptance region. So since negative 1.729 is greater than negative 1.960, except H0. Now we need to give a conclusion in terms of the situation. So over here, what was being tested was whether the mean time has changed. That was the alternate hypothesis, but we're rejecting the alternate hypothesis, we're accepting the null hypothesis. That means there is insufficient data. This is how conclusion will be written to conclude that the mean time has changed. I hope this question is clear. The times taken for the pupils in Ming's year group to do their English homework have a normal distribution with standard deviation. 15.7 minutes. A teacher estimates that the mean time is 42 minutes. Time taken by a random sample of 3 students. The year group were 27, 35 and 43 minutes. Carry out a hypothesis test at the 10% significant level to determine whether the teacher's estimate for the mean should be accepted. Okay, so first I'll state the hypothesis. So the null hypothesis was a teacher estimates that the mean time is 42 minutes. So the null hypothesis will be equal to 42. And then it's testing whether the teacher's estimate for the mean should be accepted. So that means that the alternate hypothesis could be either greater than or less than. So we have a two-tailed test over here, that is mu not equals to 42. Right, now over here the data that is follows a normal distribution, so the means will also follow a normal distribution. For this, how do we find the what do we say, the mean for the distribution of sample means? We need to find the mean using the data that we have. We have these three figures, so to find the mean we'll add them up. So it'll be x bar 27 plus 35 35. So the mean will be 35 because the population mean can be an estimate of population mean is the sample mean that we did in sampling and estimation, that the sample mean is an estimate of the population mean. So mu equals to x bar, and then the variance will be 15.7 square upon the sample size, that is 3. Now how to find the z test value? We'll use the formula x bar, that is 35, minus mu, that is 42, upon root of 15.7 upon 3, 57 square upon 3. So z test is equal to negative 0.772. Now over here it's a two-tailed test, so and it's 10% significance level. So that means that this region should be 5%, that is 0.05. This region should also be 5%, that is 0.05. So from here till here the area will be this central region will be 0.9 because 10% is the significance level, so the acceptance region is 0.9. So 0.95. So the z critical value will be the value of z corresponding to an area of 0.95. So 0.95 is 1.645. Sorry. So z critical value will be 1.645. So if I erase this, it's 1.645 here and negative 1.645 here. The z test value will lie somewhere over here towards the right of, in the acceptance region, basically negative 0.772. So we can write that since z test is greater than z critical value except h naught, so what we were testing for, we were testing whether the teacher's estimate for the mean should be accepted. So we have accepted h naught, so we can say that the teacher's mean should be accepted. So there is insufficient data to reject the teacher's estimate. I'll just go over this again. So basically, we knew that a teacher had estimated that the mean is 42 minutes. We had to test whether the mean should be accepted. So that means that it's a two-tailed test. So mu h0 is mu equals 42, h1 is mu is not equals to 42. Then the distribution of sample means we found using, because it was a normal distribution, so the distribution of sample means will also be normal. Using the estimation case, the first case is that we did an estimation. So to find the mean, we can use the unbiased estimator of the mean, that is the sample mean. Sample mean will be the sum of all of the values upon the number of values. That was 35, and the variance will be deviation squared upon the number of sample, size of sample. Then we found the z-test value. Then we found the critical value, z-critical value, because z-test value was lying in the acceptance region, so we accepted h0. Next question. In Europe, the diameter of women's rings have mean 18.5 millimeter. Researchers claim that the women in Jakarta have smaller fingers than women in Europe. The researcher took a random sample of 20 women in Jakarta and measured the diameter of their rings. The mean diameter was found to be 18.1 millimeter, assuming that the diameter of women's rings in Jakarta have a normal distribution with standard deviation 1.1 millimeter. Carry out a hypothesis test at the 2.5% level to determine whether the researcher's claim is justified. Okay, so it's given that the diameter of women's rings have mean 18.5 millimeter. Researchers claim that the women in Jakarta have smaller fingers than women in Europe. So if I take h0 as mu equals to 18.5 millimeter, so because h0 will always be equality, so it has to be equal to 18.5. So h1 will be that Jakarta has smaller ring fingers. That means that their mean should be smaller than this. So mu is less than 18.5 millimeter. Then the second step will be that using the sample data we find the z-test value. So sample was of 20 people. The mean of the sample was found as 18.1. So we can say that x bar follows normal with mean as 18.1, and the variance will be, the deviation is given of the population as 1.1. So we can use the population's deviation, square it, and then divide it by the sample size to get the variance. Now to find the z-test value, test statistic, so that will be x bar 18.1 minus mu, that is 18.5, upon root of the variance. So z-test is equals to negative 1.626. Now over here it's lesser than, the alternate hypothesis was less than 18.5, so we'll have a lower tail test. So, and it's 2.5%, so let's say that this region is 2.5%, that is 0.025, the area. So the rejection area is 0.025, and the acceptance area will be 0.975. Now we need to find the z critical value. What we can do is, because the graph is symmetrical, so we know that if we take this value, let's say this is a, let's say just z, then, and the area behind it is 0.975. If the yellow region is 0.975, then the value of z that we'll get will be the same as the z critical value, but it will just be positive. So we can find that and then just convert it to negative. So I'll find the value of z with area 0.975 and just change the sign to negative. So 0.975 gives us a value of 1.960. So z critical value is 1.96. Negative 1.96 we'll take because it's on the left hand side. Now since negative 1.626 will be towards the right of that, so it's in the acceptance region. Since the z test value is greater than the z critical value, accept h naught. Now in terms of the situation, so the researchers' claim was that the women in Jakarta have smaller fingers. That was the alternate hypothesis, but we've accepted the null hypothesis. So that means that we're rejecting the researchers' claim. So there was insufficient evidence to accept the researchers' claim. Because the researchers' claim was that the mean size is smaller than that, but we're not accepting that. So there was insufficient evidence. I'm just writing insufficient evidence. To accept researcher's claim. I'm just writing claim. I hope this question is clear. The last question for the testing. The manufacturer of a tablet computer claims that the mean battery life is 11 hours. A consumer organization, mean battery life is 11 hours. Consumer organization wish to test whether the mean is actually greater than 11 hours. So I'll just write the null hypothesis. Mean is equal to 11 hours, and alternate hypothesis, mean is greater than 11 hours. They invited a random sample of members to report the battery life of their tablets, then they calculated the sample mean. Unfortunately, a fire destroyed the records of this test except for the following partial document. So there was this document that had the sample size, it had the sample mean, it has written that the result is significant at the 5% level, but it's not significant at the 2.5% level. Given that the population of battery lives is normally distributed, with standard deviation 1.6 hours, find the set of possible values of sample size n. Right. So you'll find the possible values of n. We have this. Okay. So firstly, let's say that the variable was x. So x bar will follow normal. The mean we have as 11.8, and that's the sample mean, which is an unbiased estimate of the population mean. And then the population variance would be 1.6 square upon n, because we don't know the value of n, the sample size. Using this, we could find the z-test value. So 11.8 minus 11 upon root of 1.6 square upon n. This will be 0.8 root n upon 1.6. That is 0.5 root n. Okay, so now they're saying that the result is significant. Okay, so what they were testing was that the mean is actually greater than 11 hours. So what they're saying is that at the 5% level, the mean is greater than 11 hours, but at the 2.5% level, the result shows that it is not greater than 11 hours. So over here, it's a one-tailed test because it's only greater than. Let's say this is. Okay, so over here we have two possible regions. One is 2.5%, one is 5%. So let's draw this. This is z critical value. This is the 2.5% level. So what this means is that this area is 2.5% or 0.025. Then there is another one. Let's say this is the critical value of z at 5%. So this means that this region is 5%, that is 0.05. Now what we need to do is we need to find, basically at the 5% level, h1 has to be accepted. So but that means that at the 5% level the test value should lie in this region, whereas at the 2.5% level it's rejected. So that means that it should be towards the left of the 2.5% level. So that means that it should lie in this region. So if we can find these two critical values, then the value of the z test should be between them. So for 5%, first I'll find the critical value. So if we ignore this, so now considering this region, because towards the right is 5%, so this region will be 0.95. so in the z table we can go to 0.95. the value corresponding to that is 1.645. so over here the z critical value is 1.645. right. Then now we'll find the second critical value. So in that case, let's ignore this. So this area will be 0.975. The critical value corresponding to 0.975 is 1.960. So we've got the two critical values. Now what we need to do is that the test value should lie between these. So 0.5 root n should be greater than 1.645. That gives us n greater than 10.8. Whereas 0.5 root n should be less than 1.960. That gives us n less than 15.4. So n is, because n has to be an integer, so it's from 11 till 15. I hope the testing for the normal case was understood. I'll go back to the syllabus. So from the syllabus, we've done the first point, covered these points, and we've done the third point. Now we'll move on to the fourth point and part of the fifth point. Okay, so that is about errors. So firstly, let's understand what errors are, possible in hypothesis testing. There are two types of errors. One is type 1, one is type 2. Okay, so this is a simple table. The first possibility, when we're doing carrying out a hypothesis test, there are four possibilities. The first possibility is that the h0 that we have, the null hypothesis that we've given, that is true. If that true null hypothesis is accepted, then there is no error, because it was a true statement that was accepted. However, if the true null hypothesis was rejected, it's written over here as well, true null hypothesis was rejected, then that is a type 1 error. So there was a true hypothesis, true statement, but that was rejected, so that's an error. That is called a type 1 error. And then the second possibility is that the null hypothesis is false, the statement was not correct. If the false statement is rejected, that is this box, then that is again no error because it was a false statement that was rejected. However, if the false null hypothesis was accepted, then that is a type 2 error. When H0 is false but it is accepted, that is a type 2 error. Right, now I hope you've understood the basic concept of the two errors. Now applying those to the normal distribution. So the type 1 error, that the statement of type 1 error was that there is a true null hypothesis that is rejected. So in our normal distribution is working, what we used to do was, just go back to, sorry. Yeah, so over here, the significance level was the rejection of H0. So even if H0 was true, the significance level gave the probability of rejecting that true H0. So in a type 1 error, a true H0 is being rejected. So the probability of the rejection region or the significance level directly gives the probability of a type 1 error, because the true H0 is being rejected. So again, the significance level gives the probability of the type 1 error. So that is simple. However, for type 2 error, so over here, when we're calculating type 2 error, this will get more clear in the question that we attempt. So basically over here, the H0 that we initially had was false. Now we'll be given a true H0, the true H0, and based on that, we'll have to find the probability of the false H0 being accepted. So we'll be calculating the probability of the acceptance region of the false H0 with respect to the true H0. So for example, if I just explain it briefly. So this was the graph initially, and the mean of this was H0, but this was the false H0. I'll write H0 F. Now and over here, let's say that this was the critical value. So this was the acceptance region. Now the true H0 lies, let's say, somewhere over here. So the new distribution will be, just a second. The new distribution will be somewhat like this, where the mean will be over here. This is the true H0. So now what we'll do is, we'll forget this curve. Let's make this bold. And let's make this okay, never mind. So the graph we'll be focusing on is this graph now. This is the true graph, the true normal distribution curve. So with respect to this, we'll be finding the probability of the false H0 being accepted. So we'll be finding the probability of this region. I'll use a different highlighter. So we'll be finding the probability of this region now. that is the region behind the critical value. That was the acceptance of the false H0. However, now this graph does not apply. Now the graph that applies is this graph, the one towards the right, the new graph. So with respect to that mean, we'll be using the normal distribution theory to find the probability of the acceptance region of the first H0. This will get clear in the questions, I hope. Okay, so the first question, people who diet can expect to lose an average of 3 kg in 1 month. In a book, the author claims that people who follow a new diet will lose an average of more than 3 kg in a month. The weight losses of 180 people as a sample size. The mean was 3.3 kg and the standard deviation was 2.8 kg. Test the author's claim at the 5% significance level, stating a null hypothesis and alternate hypothesis. First part is about testing hypothesis. So the H0 will be mu equals 3 kg because we always go for equality, and H1 will be mu greater than 3 kg. Now we'll use the sample to find the test value. That will be the mean of the sample, 3.3, minus the H0 mean upon the deviation, 2.8 upon root of the sample size. So this test value is coming as 1.44, and it's a 5% significance level. So if I draw the curve, it's an upper tail testing because it's greater than over here. So the the critical value, this region should be 0.05, so this region should be 0.95. From the z table, the value at 0.95 is 1.645, so this is 1.645. 1.44 will be towards the left, so since 1.44 is less than 1.645, except H0, and there is insufficient evidence the claim was that more than 3 kg. So there's insufficient evidence, the author's claim is being rejected. So there is insufficient evidence to accept author's claim. Then state what is meant by a type 2 error in words relating to the context of the test in part 1. So what would a type 2 error mean in context to this test that we did in part 1? So type 2 error is when the null hypothesis is wrong but it is being accepted. So a type 2 error would mean that even though the null hypothesis is wrong, that the mean is equal to 3 kg, we are still accepting it. Means that even though the weight loss is more than 3 kg because the null hypothesis is wrong, so even though weight loss is greater than 3 kg, because that is, we're rejecting it if H0 is wrong, even though weight loss is greater than 3 kg, we conclude that it is not. So again, what we did over here was that even though the H0 was h naught was wrong because it's type 2 error, so h naught, that is mu equals 3 kg, was wrong. So that means that mu is greater than 3 kg. So even though weight loss is greater than 3 kg, we conclude that it is not. That is type 2 error. The weights x kilograms of bags of carrots are normally distributed. The mean of x is mu. An inspector wishes to test whether mu equals to 2.0. So h naught will be mu equals 2.0 and h1 will be mu is not equal to 2.0. He weighs a random sample of 200 bags and his results are summarized as follows. So first we'll find x bar, that is 430 upon 200, 2.15. Then we'll find s square, because over here the population variance is not given, so we'll be using the unbiased estimate of the population variance. That will be 200 upon 199 times 1290 sigma x square upon 200 minus 2.15 squared. So s squared is equals to 1.836667. Now the first part is carry out the test at the 10% significance level. So first I'll draw the graph because it's a two-tailed test. So it's 10%, so this should be 0.05 and this should also be 0.05. The central region will be 0.9. So from here till here it's 0.95. The value at 0.95 is 1.645. That means that this is 1.645. This is negative 1.645. So we've gotten the critical values. Now we get the z-test value from the sample data. So x bar is 2.15, mu is 2.0 upon the deviation 1.8367, deviation upon the root of the sample size. That is equal to 1.565. 1.565 will lie somewhere over here in the acceptance region. So we'll be accepting h naught. So there is insufficient evidence to say that mu is not equal to 2.0. We can say that, right? Because h naught is accepted. Right, so in the second part, they're saying you may now assume that the population variance of x is 1.85. Spectre weighs another random sample of 200 bags and carries out the same test at 10% significance level. State the meaning of a type 2 error in this context. So a type 2 error is when the null hypothesis is wrong but it's accepted. The null hypothesis, that is 2.0. So the answer could be that even though the mean weight is not 2.0, it is accepted, or it is accepted as 2.0 kg. So it's not in kg, yeah, kilograms. So that is part A. Then for part B, they've given that the true mean is 2.12. Show that the probability of a type 2 error is this. So you have to find the probability of a type 2 error. So let's go to a new page. But in fact, I'll copy this first. Okay, so this was the initial graph. Now over here, just a second. Yeah. So the mean over here that we'd use was 2.0. Now what we need to do is that we need to find these values 1.645 and negative 1.645 are values of z. What we need are the values of x bar so that we can compare that with the new mean. Right, so what we'll do is we'll use this formula z equals to x bar minus mu upon sigma upon root n with both negative 1.645 and positive 1.645. Mean was 2 because we found this with mean 2. Sigma was given as 1.85 in this testing and root of 200. So this will give two values of x bar. The first one is 2.158 with positive and 1.842 with negative. So the x values over here are 2.158 and 1.842 and the mean is 2.00. Okay, so just a second. Yeah, so this was the initial graph with mean 2.0. However, now we found that the actual mean was 2.15. It was shifted towards the right. So the actual mean was somewhere over, let's say here, 2.15. So the new graph will be somewhat like this with the mean, I'll draw it with yellow, as 2.15. 2.12. So now what we need to do is, now the acceptance region for the false H0 was from here till here between the two red lines. So we need to find this area now with respect to this new mean of 2.12. Okay, so what we can do is, so basically now this area will be represented in a different way because the new normal distribution curve is the one that is bold, that is not dotted. So the area will be under that curve and not under the dotted curve. The area will be like this. If I extend the red line till here, the area will be in this way. So I need to find the area from 2.158, the probability from 2.158 till 1.842. So we need to find the probability of from 1.842 till 2.158. That is probability of x less than 2.158 minus probability of x less than 1.842. That is probability of z less than minus 2.12. Now it's with respect to the new mean, so we'll use 2.12 as mu upon 1.85 upon root 200 minus probability of z less than 1.842 minus 2.12. So this is probability of z less than 0.290 minus probability of z less than minus 2.125. This is phi of 0.290 minus 1 minus phi of 2.125. Phi of 0.290 will be from the normal distribution table 0.6141 minus 1 plus phi of 2.125, 0.9832. .597. Because I made a mistake over here. This is the variance. This will also be under root. So that will give 0.397, 0.397 and the other value will be minus 2.89. So phi of 0.397 is 0.6543 and phi of 2.89 is 0.9981. .652. I'll go over the question again. It was a bit complicated. So first part was simple, second part A was simple, second part B. So over here, what we had done was in the first part we had worked with, we had taken null hypothesis as 2.0 and then we had found we had tested for it, and the acceptance region was from 1.645 to negative 1.645 values of z. Using this, we found the values of x for which this hypothesis was being accepted. So for that, we use z equals to x bar minus mu upon sigma root n. The working is done over here. So in that way, we got two values of x bar that were the acceptance region. They are shown on the graph as 2.158 and 1.842. So this was the acceptance region. Now the new mean was 2.12. So the distribution was shifted towards the right. Now we found the probability of the acceptance region, that is from 1.842 to 2.158, with respect to this new distribution. So now in that working we used mu as 2.12, and then that was simple normal distribution working. So I made a small mistake, but otherwise it was simple, and just use that to find the probability of that region. I hope it's... The next question: over a long period of time, it is found that the time spent at cash withdrawal points follow the normal distribution, with mean 2.1 minutes and standard deviation 0.9 minutes. A new system is tried out to speed up the procedure. The null hypothesis is that the mean time spent is the same under the new system as previously. It is decided to reject the null hypothesis and accept the new system is quicker if the mean withdrawal time from a random sample of 20 cash withdrawals is less than 1.7 minutes. Assume that for the new system, the standard deviation is still 0.9 minutes and the time spent still follows the normal distribution. Calculate the probability of a type 1 error. So type 1 error is basically the significance level. They're the same thing. So the probability of type 1 error is equal to this significance level. So you have to find the percentage of the significance level. So what they're saying is, okay, there is a... Let's first write the hypothesis. So the null hypothesis is that mu equals 2.1 minutes, and the alternate hypothesis is that mu is less than 2.1 minutes, because it's saying that the new system is quicker, so that means that the time spent will be lesser. So mu is less than 2.1. Right. So if this was the graph with mu as 2.1, so they're saying that if the mean withdrawal time is less than 1.7 minutes, so let's say that this is 1.7, if it is less than 1.7, that means that this region, then that will be, then the null hypothesis will be rejected. Means that this region will be the rejection region because the null hypothesis is being rejected. So you have to find the probability of this region. So we'll find the value of z for this. So that will be 1.7 minus 2.1. Basically we have to find probability of x less than 1.7, which is equal to probability of z less than 1.7 minus 2.1 upon the deviation is given as 0.9 and the sample size is 20. So this is probability of z less than minus 1.988. This is the same as 1 minus phi of 1.988. So 1 minus phi of 1.988, 0.9766. Zero point 0.0234. So this is the answer to the first part. Right, now the second part, if the mean withdrawal time under the new system is actually 1.5 minutes. The actual mean is 1.5 minutes. Calculate the probability of a type 2 error. So what's happening is that let's copy this. So initially we were assuming that the mean was 2.1, but that is wrong and the actual mean is 1.5. So the new graph will be somewhat like this with mean 1.5. Let's say this is 1.5. Now we need to find the probability of a type 2 error, that is the wrong hypothesis being accepted. For the wrong hypothesis to be accepted, the acceptance region was greater than 1.7. It was this region. So we need to find the probability for the new distribution, that is the bold line, not the dotted one, the bold one, to be greater than 1.7. So basically the probability of x, which is the new one, greater than 1.7. This will be equal to probability of z greater than 1.7 minus 1.5 because we're taking the new distribution now, so it will be 1.5 as the mean upon 0.9 upon root 20. So probability of z greater than 0.994. So that is 1 minus phi of 0.994. Phi of 0.994 is 0.8399. Zero point 0.1601 to 0.160 to 3 SF. This is the second part. I hope it's clear. Now the next question, the last question. The number of cars caught speeding on a certain length of motorway is 7.2 per day on average. Speed cameras are introduced and the results shown in the following table are those from a random selection of 40 days after this. Calculate the unbiased estimates of the population mean and variance of the number of cars per day caught speeding after the speed cameras were introduced. So for the population mean, we'll find x bar, that is 4 times 5, 20, plus 35, plus 48, plus 70, plus 40, plus 18, plus 30 upon 40, because the total 40 days. So this will be 6.53. And then for s square, that is 40 upon 39. Now sigma x square will basically be 4 square, because that is the value of x, and then the frequency is 5 times 5 plus 5 square times 7 plus 6 square times 8, and so on, upon 40 minus 6.53 squared. So this, I'll do it directly in the calculator. It's coming equal to 2.87. Then they're saying, taking the null hypothesis h naught to be mu equals to 7.2, test at the 5% level whether there is evidence that the introduction of speed cameras has resulted in a reduction in the number of cars caught speeding. So h naught is mu equals 7.2, h1 is mu is less than 7.2. So it's a one-tail test on the lower tail. So z test value will be, the mean is 6.53 minus 7.2 upon root of 2.87 upon 40. This is coming equal to minus 2.501. This is the test value. Then for the critical value, it's a 5% test. So we'll go to 0.95, and that is 1.645. So the critical value will be negative 1.645. I can show it on a graph as well. So basically we need this value. This is coming negative 1.645. This region is 0.95 and this is 0.05. So z test is negative 2.501, so that is definitely towards the left. So since z test is less than z critical value, reject h naught. So we have to test that whether there is evidence that the introduction of speed camera has resulted in a reduction in the number of cars caught speeding. So it has resulted in a reduction. So we can say that there is insufficient evidence to say that there is no reduction, or you can say there is sufficient evidence to say that there is a reduction in the number of cars being caught speeding. Then in the third part, state what is meant by a type 1 error in words relating to the context of the test in part 2. Without further calculation, illustrate on a suitable diagram the region representing the type 1 error, right? So state what is meant by type 1 error. So type 1 error means that actually the mean remains 7.2. However, the conclusion drawn is that there is a reduction in the mean. And illustrating on a diagram, so this is a normal curve. The mean will be 7.2 and this region will be shaded, and you can label this as 0.05%, and then this is 0.95. I hope this is clear. So I'll just go back to the syllabus. So from here we've covered this point as well. We've covered half of the last point as well. We haven't covered the red wala part. We've covered the yellow part about the normal distribution. We haven't done the binomial and poisson. So that's the end of this video.